Okay, so we're going to take another look at putting a standard form quadratic into vertex form. And so just a quick reminder what vertex form is. So vertex form for a quadratic looks like this: a times x minus h squared plus k. Now each of these things, a, h, and k, tell us something about the quadratic and its graph, but specifically the h and the k are the vertex. So what we want to try to do is write this standard form equation into vertex form. And so that means we have to try to create something that looks like this out of a part of this equation. And we know that perfect square trinomials factor to look like that. So they start to get a little more complicated when the coefficient of the x squared is something other than 1. So we looked at some ones that were fairly simple in class, and this one would be a little bit more elaborate. So the first thing that we always want to do if we don't have a perfect square, though, is we want to take the constant term kind of out of the picture. Just slide it down, sort of like just put it off to the side for now. So it's not like we're getting rid of it, but we're just kind of ignoring it for now. And we're just going to focus on the terms that have the x squared and the x term. And so I have 3x squared plus 18x. And I want to try to create a perfect square trinomial out of it. Well, it makes it very difficult when it's already starting off with something that's not a perfect square to begin with. And really, when we want to create a perfect square, it's easiest if it starts off with x squared only. Not a 3x squared or a half x squared or even a negative x squared, but just starts off with x squared. So what I want to do is just factor that 3 out. In other words, divide it out. Well, when I divide it out of the x squared term, that just leaves me with x squared. When I divide it out of the 18x, that leaves me with plus 6x. Okay? So now what I want to do is I want to create a perfect square using x squared plus 6x. And so when I do that, I know that I have to figure out a constant term that I can add that is half the middle term squared. So the middle term is 6. Half of that would be 3. 3 squared is 9. So I'm adding 9 here. But what I'm actually really doing to this side of the equation is I'm really, in effect, adding 27. Because that 3, if I were to go and distribute it back through, would turn this into plus 27. So because of the addition property of equality, I know that what I have to do is go over to the other side of the equation, and I have to add the exact same thing to the other side, which is 27. So the net effect of the 3 times 9 is now matched over here on this side to keep it in balance. Okay? So now I'm going to go ahead and take this perfect square that I just created, and I am going to factor it down so that it looks like this part of vertex form. So I know that when I factor a perfect square trinomial, and I know this is 1 because I created it so it was 1, I take the square root of the first term, which gives me x. I take the square root of the last term, which gives me 3. That gives me my 2 terms, and then the sign always agrees with the middle term. So this is a plus 6x, so this is going to be a plus here. So now that 3 out in front still has a part to play. It's very significant because it's actually telling you the vertex is stretched. That the parabola is stretched by a factor of 3. And now I have to clean up the rest of the loose ends because I want this to just say f of x equals. Well, right now on this side I have f of x plus 27. So I'm going to go ahead and subtract 27, and that means I have to subtract it from the other side. Now I have f of x left here, and the effect of subtracting the 27 here makes that plus 1. So now that's in vertex form, and I can just look at it, and I can read the vertex is whatever makes this equal to 0. In other words, the shift 3 units to the left, because x lies to you. So that's left 3, that's negative 3, and then up 1. So the vertex is at negative 3, positive 1. And this also is a vertical stretch of 3. That's it for this example.